live.
All right. Well, welcome again. I'm here with Race, who's just outside at the View, and we have a very special guest today, Rick Lammers from Groq, and that's Groq with a Q.
I'm not sure if you can see it.
So this is the Groq. How should I describe Groq?
Groq is a company. They're based in Mountain View. They've been going for over 7 years, and they make their own processors. And their processors are focused on machine learning workloads. And these days, a lot of that is about language models, of course. And yeah, it's a really exciting company. I joined them a little over half a year ago. And there's a lot of really interesting work that needs to be done to make AI better. Right? Mm-hmm. So I work there on the cloud team, and I interact with the compiler, and I interact with our inference stack. So if you're familiar with something like VLLM, it's a little bit like that, but then like tailored to our custom infrastructure. And I think that's the TLDR.
Cool. So for people who are familiar with maybe like companies like Replicate or Fireworks, how does that compare? How does Groq compare to these companies?
So first of all, they are typically all just using GPUs, so off-the-shelf units that they can buy, that anyone could buy. Mm-hmm. And they also often projects like VLLM or TensorRT or maybe TGI from Hugging Face, which are all excellent pieces of software. But I think the interesting thing about Groq is that we have a fundamentally different architecture. So the architecture difference really changes the paradigm of also how you think about running these models and how to get them compiled and to run fast. Because it's not just about tokens per second, which we're leading by a very large margin. If you look at artificial analysis, which is a really good benchmarking website, you can see how big the gap can get if you build an architecture, a computer architecture that is specifically optimized for inference. But the big difference, I think, from my point of view, biased for like what I do day to day, is that we don't have to operate at the level of all these kernels that need to be implemented that are kind of memory aware and kind of operation aware in order to get the efficiencies you need. So often you would see like specific kernels, flash attention, implementations, just to get like good performance from the GPU architecture, and it's almost like you're hacking a GPU architecture in order to get good inference. And what we have with Groq is we have no complex multi-hierarchy memory system. And so what you see with GPUs is that you have to really be aware of like when am I kind of skipping over some of these cache boundaries where you're going into slower memory, more global memory, or even if you need to interact with the host memory. Mm-hmm. And with Groq, we have SRAM memory on chip and a very flat architecture, and that means in practical terms that the compiler can reason itself. So our improvements happen on the compiler, and we don't have to do any sort of manual optimization. So practically speaking, we compile PyTorch computational graphs or anything that can be represented in Onyx and run it on the chip by compiling it to run as efficiently as it can squeeze it into the available compute and memory that the PCIe cards offer.
Yeah, so this is kind of a nice bridge from our previous interview with Chris Ladner earlier today. Chris, of course, is a founder of Modular, who has their own like compiler because he also invented LLVM back in the day, and Swift programming language. So you're saying like that one part, because like I think if the people who are familiar with Groq, they are familiar with like the chips. But as I understand you correctly now, it's just more than that. It's also like a whole compiler that's optimized for specifically this chip.
Honestly, it's really the synthesis, the marriage between the compiler and the hardware. So the way to explain it is, so we have a name for it. It's like a fully deterministic architecture, and what's meant by that is that because we don't have these complex memory hierarchies, we also don't have a lot of dynamism in timings. And so what we get is we get exact, precise timings for a large meshed network of PCIe cards for when data will arrive at what point. So chip number 476, when is it going to get the next matrix from a matmul that happens, 100 chips before it? And because we have this information and we keep this stable, deterministic guarantee stable over the lifetime of the execution, we get to reason over the entire compute graph fully ahead of time. So practical implementation or implication is we can actually compute the speeds we're getting without running it. We already know.
Say that again?
We know the speed we're getting, so the
speed,
throughput,
sure, yeah.
tokens
Yep,
per second,
yep.
and total throughput. We know that before we run anything, because we compile it and we know exactly how the compute graph is going to flow. Try doing that with a GPU. You can't. You literally can't, because you will basically need to see how your choices you made on these kernels, on the implementation, how they will affect kind of like memory pressures and kind of like all the stalling that happens. So it's a fundamentally different approach, and it isn't as flexible as GPUs. And we know that that means that there are certain things that can be harder, like swapping, LoRa swapping, for example. We can do it, but we need to like think a bit more carefully. But what we do is we go all in on the workload that most people care about, and that's running these LLM models, vision language models, whisper-based, transformer-based models, and we can then run them really fast as a result.
Yeah. But I think like most people who are watching the stream are familiar with like running their own models on their own computer, which is
very exciting.
It's super exciting, and it's kind of basic, of course. Like the model fits in your memory or it doesn't.
It is more nuanced because there's lots of different silicon, right?
Yes. So how does Groq do that? Because like I guess like this architecture is very different from like downloading Llama and running it on your GPU.
So the question is how Groq differs from local inference?
Yeah. So especially like if you think of so understand like a lot of things will happen in parallel in your system, normally like if as an Llama user, for me, like my memory is I mean, it's the simplest version, right? Of just running inference. Like your model fits in memory, and there's one GPU, and that's it. Now you have like this system with your own processor with its own SRAM on PCI cards. How can you explain for people who are not familiar with this kind of hardware like how a model gets loaded in this kind of system? Is it different than my Llama system?
Yeah, there was like an interesting just to contextualize, there was like an interesting VLLM meetup going on a few months back, and there were discussions about hardware support, like more heterogeneous hardware support in VLLM. Because there are lots of people who care about running on kind of unified memory architecture. So if you look at the M series Apple Silicon processors, they have a unified memory architecture. I'm not an expert on them, but as far as I understand, the GPU memory therefore is bounded by the total system memory. And what you then see is that if you have a very large unified memory and the model can fit, you get very decent performance. And so let's take a more traditional, maybe Windows-based system that has like an NVIDIA 4090 attached to it and maybe has 128 gigabytes of system DRAM. Here you see this approach where it's not really like a unified context, but it's more like slicing. So you kind of offload some of it to the CPU for typically the parts that don't have large-scale mathematical operations, like no matmuls, and you put parts into the GPU that have heavy computation, and then you offload the results at some point in the calculation to do maybe conversion back sampling, maybe on the CPU, of the log props that get generated from the model, and then you end up getting a token and you feed it back into the system, and it kind of loops like this, right, to generate tokens.
Because like the issue is with like Windows-based PCs, you have like your GPU with a limited amount of memory, like 24 gigabytes or something like that. for NVIDIA.
Yep.
But that's separate from, of course, your actual
Your
RAM.
system DRAM.
Yeah.
Yeah, and so for all of these different systems, so we have on the Groq side, you have all these PCIe cards that have on-chip SRAM. Then you have these unified memory architectures on laptops from Apple, and then you have these traditional gaming PCs that have pretty fast GPU cards. The ops per second they can do is very impressive, even relative to like their way more expensive server counterparts. And so this is like I think it's in a way it's really interesting, right? Because you have this very diverse, varied ecosystem of different architecture, and I think you can kind of see projects specializing towards them. So the consensus I think at that VLM meetup was we're about server-side inference. It's like there's this Olama, there's Llama CPP as a backend, and you have other initiatives. XLlama is a really cool project, and you just see that it's almost infeasible to maintain a project that caters to all of these diverse architectures. So you see this notion of, or this tendency to just like say, okay, what do we care about most, and let's optimize for this, because in the end, if you need to build a system that can generalize across all of these, it's really questionable if that's actually feasible and maintainable. Like who's also going to like keep everything up to date, because all of these things are also moving targets, right? Like NVIDIA's innovating, Apple's innovating with the APIs they expose, and kind of features that are supported, native, certain precision operations, right? Like a lot of things around compression, native decompression, like all these different kinds of details that also keep improving, luckily, on all these different platforms. So I think in terms of scope, people need to like scope projects down, and that I think is a good thing, because then these projects actually work and ship and become stable and reliable, and you can build stuff on top of it. So yeah, I think there's healthy, good, interesting innovation happening across inference engines for all these different hardware architectures.
Yeah. Hey, and when we talk about Groq, we talk about performance, right? I mean, you already mentioned like the performance is kind of out of this world. To be honest, I mean it's not just a little bit faster than the competitors, but it's like
So some latest numbers, like 1,250 tokens per second for Llama 8B, which is 8 billion parameters.
Which is still a small model, but still. But
and that's for single user, right? And I think this is you saw this company Etched announce a new ASIC chip.
Was it the rendering that they had of the...
I think they had an image of it, and they announced it 500,000, right? 500,000 tokens per second. But the headline didn't really talk about what that was obviously not the per user number, is my guess. I don't know, but my guess is it's not the per user number, it's just the total throughput number for eight of those edge cards.
That we have like this.
Well, I mean, if you're
right?
packing 64 users or 128 users into these chips, and then you just have 100 tokens per second, you multiply it by 128, and you get the throughput for the whole thing. But it's like they're running independent sequences for the transformer, right? And so what I think is interesting is that you need to also look at the total throughput of the system to look at the economics, and then you get a really fair argument of like, okay, this is how much the hardware cost to purchase, then you have the hardware cost to operate, and then you have, as a consequence of the performance characteristic, what can you charge for tokens and have a good margin, right? And I think what you need to not forget is that you can easily optimize throughput a lot, but come out with like 5 tokens per second generation speeds. And this is actually some slides of some of these presentations where it's like, we do so many 100,000 tokens and we'll be super cheap, but you'll have such a slow inference that nobody wants to actually use that API, right? Because a lot more innovation is going on at the application level of what can we do with additional token budgets, right? If we can do 1,000 tokens per second, how can we build our app differently? And so at Groq, we're really focused on maintaining both at the same time. We're stretching, right? It's like more throughput, so we have better economics, but we never sacrifice user token speeds, right? And that's I think a much harder game, because that's a trade-off game where you're constantly trying to find the best balance of both. And I think the internal team is just doing phenomenal work, constantly pushing up throughput without sacrificing individual tokens per second. And I think people who are not like so aware of this trade-off surface might just like see headline numbers and forget about that reality. But as long as you don't know both answers, you don't know, okay, if you're getting more throughput, but what are you sacrificing on speeds, per user, then you have half the picture.
Yeah,
right?
yeah. Now, I guess, I mean, if a company announces something today, it will take a while before they have a whole server farm up and running. There is time between like an announcement and rolling out the chips, getting everything installed, make the chips,
install the chips.
You probably also need some kind of compiler that works with that just like you guys have.
Yep.
And you already have this. This is running right now. So by the time they will be up, we can expect probably something like
we'll be a few leaps ahead,
or whatever.
Right?
Yeah. So let's talk about benchmarks, because that's something you have been working on or been thinking of as well, I understand. What is the issue right now? Because we have benchmarks, right, for LLMs. Tell me.
So I can bring it back. So a lot of what I just talked about, also just a caveat, like this is my understanding about what Groq, what we're doing at Groq internally, but these are not specifically the areas I work on the most. Like these are mainly existing teams, existing engineers, the compiler people, the silicon people who are working on these things. My work at Groq is focused on function calling or tool use in particular. And I think it's a very exciting area, and we need to. So at Groq, we run open source models and make them available through an API, so you can use them.
Yeah, we didn't mention that, but yes, yeah.
Yeah. So we're extremely invested in the open source ecosystem, and we're always trying to find ways to help improve the quality of that ecosystem. So if we have findings, like we did at this conference with my talk, talking about evaluation suites and how those evaluation suites could be made better, and how you can train better models by using the results of that evaluation suite. That was what my talk was about. But just the summary of my current take on these evaluations is that you need to know how, like if you need to choose between models, which one to use. There are clearly the on-paper trade-offs, right? Like there certain sizes implicate tokens per second speed. A 70B will be slower than an 8B. But what you want is, if you're building an application that depends on function calling or tool use, you want to know how well does this model perform at that task. And of course, you can build your app, write your own evals, but then it's like you kind of want to know up front, kind of like where you should be looking.
So is there something like an existing scoreboard for that? Right now?
Yeah. So for people who are not familiar, there's one project in particular that I think is really worth paying attention to. It's called the Berkeley Function Calling Leaderboard, or the Berkeley Tool Use Leaderboard. And it's an open source project by a group of Berkeley students. And they've done excellent work in trying to just kind of categorize the major categories of tool use. So you have kind of these different modes. So a lot of the breakdown of their tool use benchmarks, if you check it out, are on, for example, simple tool use, where you just ask a question, get a single tool back. That's like the base case. And then you have multiple tool calls, where you ask a question, it needs to use a tool. You ask a follow-up question, might need to use a different tool or use the same tool differently. You also have parallel tool use. So you ask one question, maybe you say, what's the weather in New York, San Francisco, and Tokyo? And then it needs to like fetch the weather for 3 locations, but it can do that. It can like generate the calls to do that at the same time, because you can get the weather for 3 cities simultaneously. And so there are all these questions, also tools that requires input, maybe code. So if you have a tool that says, SQL, run SQL tool, the input arguments start to become more complicated, because you now need to go generate SQL that goes into the function that can run, and then it needs to like be correct.
Yep, and not like hallucinate any
table names. So like tool use with complicated inputs is like a really hard thing for models to do well, because it needs to pay attention to multiple things, and it needs to pay attention to the fact that it needs to respect JSON schema specification of a tool. So tools allow you to define what are the arguments that are valid for calling this function. Once that result comes back, it's in some format, and it needs to like interpret the result and maybe use that to do another tool call. So maybe it's an error, and maybe it needs to understand the error. So the Berkeley benchmark is really kind of like trying to capture a lot of the common cases that people throw against it, and then you can kind of see like which models support all these different variants, and does your use case look a little bit more like this category or that category, and then you can start to get an intuition. And one of the things that I think a lot about, and also that my talk kind of went into, is this idea of system one, system two thinking, where you have LLMs, which are really powerful associative reasoning systems from my point of view, where they can reason about a situation based on their pre-training data. They see patterns and correlations, and they kind of reason in terms of probabilities, like, okay, I've seen this in the past before, maybe he means this thing, and so I'm going to complete it this way. And that is a really powerful mode of reasoning, but it is also not a great mode of reasoning for a lot of very symbolic, logic-based, mathematical, exact types of reasoning. So that's typically referred to as systems two reasoning. And computers are really good at that, right? Like, you can really give a very long, complicated mathematical problem to something like Mathematica, and it can do an excellent job like solving that with symbols, with logic, with deduction. It's all built into these engines. And so I think what I would like to see kind of like as a next step in the benchmark evaluation landscape is, can we start to quantify the performance of language models that in a way marries kind of like measures the entire composed system instead of just the LLM in isolation. Because imagine a hypothetical scenario, we have two LLMs, and one is really good on paper for like the typical evaluation benchmarks you see, that only measures purely the LLM's performance on text completion. So it doesn't have access to anything outside. It's just like really good at like emulating a calculator, and you can ask it some math questions, or like on the math QA or some math benchmark, it does really well. And then there's this other model, and on paper for those kinds of tasks, it looks like it's worse. But maybe what you actually want to know is, how well does this LLM perform if you pair it up with a set of tools that can take care of that system two thinking, right? And there's this kind of paper that I think kicked off a lot of these ideas. It's called Toolformer. It's a
Toolformer, like
Toolformer.
Okay,
it's
sorry.
like transformer with tool.
Yep.
Symbolizing this idea. I didn't come up with that marriage of like these kind of different modes of reasoning. Other smart people came to that conclusion also. And what you then can do is you measure the total system performance, right? Both the LLM paired with a set of tools that can do reasoning tasks that you care about for your use case. And then maybe that other model wins. I mean, that was kind of my point of the story. It's like, you have two models on paper measuring just the LLM, it might look worse, but then maybe if you measure total system performance. And so this is what I'm really interested in, is like, can we optimize open source models, even open source foundation models, to be focused on more or less total system evaluation, and kind of like, maybe if those LLMs are better at using tools, then maybe they don't need to score as well in math benchmarks. Maybe if they're really good at reasoning and delegating, they can just be really good at tool use.
So maybe we've been evaluating the wrong things in models.
Yeah, because you get what you optimize. You optimize. You get what you measure for. So if you're measuring for just the LLM performance, that's going to probably go up. Not sure if it like plateaus, because there's always like a kind of moment where it's very hard or expensive to improve the system further.
Sure.
Maybe like data saturation, S-curves, like scaling, when the scaling stop. But I think if we start to measure the right thing, which I think application developers care about, which is LLMs that are enabled to interact with tools that are not like LLMs, but can do information retrieval, calculation, symbolic evaluation, and you measure the entire system, then I think we can actually get much further with open source models and build more reliable and higher performing end user applications. Because at the end of the day, it's been a theme at the conference, like we need to think about, where is AI going to add value? What is it going to automate? How is it going to make lives easier? How is it going to make lives more enjoyable, more efficient? And that's going to come from end user apps, not just LLMs operating in a vacuum.
There's definitely like a swift swift in thinking about like AI that happened like the last couple of months. So what do we need for that? So what how does this look like? Do you have like any architecture in mind how this can be achieved?
So I think there's definitely a need for some standardized, probably as an open source project, just kind of something that
So we're not talking about Groq, just Groq then?
No, so I would say this is more like just my personal view on like what I think should happen, and I don't know what Groq's position in that. I'm not speaking for Groq. I'm me, and I work at Groq. But what I think is useful is stuff like the OpenAI evals on GitHub that is fully open source, and people can contribute to this, and then you can use that as a benchmark to see kind of how things are performing. And I think one of the ideas that I've had is like to have a common set of tools, like, I don't know, maybe common tools or whatever, and they are they kind of like are included in a runtime where you just have these tools that do these common operations. Maybe it's like a code interpreter that can do Python evaluation or JavaScript evaluation, and maybe it's like a file system that it can like write text files or open files or do manipulations. Maybe it has PDF functionality. It can do PDF splitting, PDF reading, OCR. Like it can do like all these things, and we can like kind of standardize on a set of tools, and then you can say something about task performance of an LLM paired with a specific snapshotted, like fixed version of the set of tools. So maybe you kind of shrink wrap it and you say this is Common Tools 1.6
Right. Container,
and you
like
say
for,
like, okay, how does Llama 3B perform with Common Tools 1.6
Yep.
on all these benchmarks? And then you can start to talk about like what's composed system performance instead of what is like the individual LLM's performance. And I think what's really cool about the Common Tools kind of notion is that I know there are a lot of people who would like to see these LLMs become more useful in their daily lives, and a lot of local inference is becoming more feasible. So you can also equip your local inference with this set of Common Tools. And I know that like, people do lead code and like they do these micro optimizations. If I change this code, it will run the thing a bit faster. So like if you have this common set of tools and everyone can contribute, like maybe by the 10th iteration or the 10th month, some contributor will find a super fast PDF splitting or super fast local OCR, and then you have like an even better set of common tools, right? And I think that's like the kind of contribution that's maybe a little bit easier than making a model better, because maybe you don't have money for GPUs, maybe you don't have money. So I think like in ease of accessibility of contributing to better LLMs, I think there are a lot of developers with good ideas, but without resources. And if you like let them invest in the system 2 part, and then the system 1 part is maybe a little bit more reserved for like labs or people who like have the money and resources to make those things better.
GPU rich or whatever.
Yeah,
Yes.
then you can still kind of both collaborate and like make these systems better.
Yeah, that sounds like an incredible good idea, actually.
Okay.
So if people who are watching the live stream are interested in common tools, how can they find you? How can they? I mean, is this like just an idea, or is there?
I mean, I got this idea, to be honest, like totally fair. Like I got this at the conference while I just was working on my talk.
Fantastic.
So if people are interested, hit me up. We can make a Discord or whatever, and we can talk about how this could actually take shape. I think it's a really interesting project. I don't know if it's going to work, but you know, worth trying.
I think it's absolutely worth trying, especially like with everything going towards like agents and these kind of use cases.
Yeah, agents need tools, right?
Yeah.
And there,
Yes,
I mean,
exactly.
I will also do a shout out to some existing initiatives that I really think are really cool and work. So there's this company E2B, which I think is an agent platform. I think they're a sponsor here.
Yes, yeah,
I'm not personally affiliated with them, but I've just seen the work they're doing, and I think they have interesting ideas.
Yeah.
They offer this kind of as a runtime in the cloud, and maybe that's what you want. You want like a hosted offering, and I think there's room in the market for that. I'm more thinking about like a local embeddable, like a WASM runtime, like that you can run pretty much everywhere.
Yeah.
But yeah, I think like there are good ideas here in this area, and so I think it's just like, can we collectively come up with something that is just gonna like superpower these LLMs with the right tools?
Wow, that's super amazing. So people follow Rick, and I mean, I would love to follow like how did this will develop, because it's something I guess we really need. Just not like the small focus view on just the LLM.
And we need people to also like pitch in, because what I've seen in these open source projects like Llama CPP, contributions around LangChain, just all these like open source initiatives, they make things much better. Like any individual person just has, you know, some good ideas and then maybe not much more. And I think collectively you can just like move so much faster. I see VLLM is a perfect example. You see the ideas people are bringing to VLLM on like prefix caching, on quantization schemes, on Dockerization, containerization. It's just open source moves way faster than any other individual could ever, and even most private organizations. So I think that's where, if we want to continue to see these techniques improve, we need to use the power of open source.
Yeah. No, that's a fantastic ending, I think, of this talk. If people are interested more in learning more about like the state of open source models, or open weight models, we interviewed keynote speaker Simon Willinson yesterday. That talk was
Simon's
also
great.
He's awesome. Yeah, the interview was great to do. So you can find that on my or Ray's feed on Twitter. I want to thank you so much for making time for this. Yeah, and to end the interview, I have to actually grab Ray's computer because he just walked out. He was needed elsewhere. So I'm gonna click on this button, and then we're off. Thanks so much for everyone for joining.
Bye, everyone.